This is the demo video 1 part 2 for Team 4. So in this part of video, I will introduce the packet processing design. Um, since one of the important part in our project is the IDS design, and in our project, the convertible FIFO plays an important role. So in previous lab A, we are required to design a convertible FIFO that can um, connect the network PGA data path and our network processor where the package go into. However, in lab A, we didn't implement the drop FIFO mechanism, which is very important in our design. So what we do here is to emulate what the drop FIFO design in the IDS D. So so first um, we we rewrite the uh, drop FIFO by Verilog, which is the same room as the schematic in the mini IDS design. So in the IDS design, what we did to drop the malicious packet is to move the right pointer to the FIFO of the FIFO to the hand of the packet. And only when the read pointer is not equal to the hand pointer and the Y pointer of the FIFO can we read the packet from the FIFO. And only in this case, the packet is valid. So as you can see in this drop FIFO, we are basically do the same things. The re-enable signal is when the FIFO is read and the ring pointer is not equal to the hand pointer and the ring pointer is not equal to the right pointer and the FIFO is not empty and the wide enable is when the FIFO when the FIFO is right is when the FIFO right signal is set and it is not full. And you can see here when it is the first word or the last word packet, the Y pointer will move to the hand pointer. And if the and we will increase the Y pointer and the ring pointer when the FIFO is enabled to write or read. And only when writing we increase the depth, and only when reading we decrease the depth. And the second part is we verify the drop FIFO design by integrating it into the NetFPGA data data path. So what we did is basically the same as mini IDS design, but in a more simple way. So basically it is so basically it is a final state machine to check the packet based on the control signal, which is the most significant AB of a word. So you can see here. So you can see here. Um, the if the in control data is not equal to 0, then the so our final state machine have three states: start, handler, and the payload. And if this in control b is not equal to 0, then the state machine will change to the handler state. And if the in control bit is now equal to 0, which means that we are now in the payload. So we will go into the payload state. And and we use and and we use the begin packet signal and end packet signal update the update the hand pointer to give space to the ring pointer to read out the packet. And as you can see here, um, the out ready signal is assigned to the 5 ring, to the 5 ring, and then as well as the 5 is not empty, we will have out write signal to the downstream module, and in ready signal is generated as long as the depth of the 5 is smaller than 5 minus 2. And you can see we need to latch the input data signal, and we verified it in the NetFPGA as a router successfully. So I will load the bit file first. And as you can see, we can ping between the different nodes. So it is integrated into the NetPGA data path successfully, and it can work as a router. And the third part um, is after the entire packet is loaded into the FIFO. And as you can see in the lab A, so we need a controller to tell the precise processor to process the data. And what we did is to add a pre CPU state after the payload state to generate a signal named CPU mode to indicate that now we are using the FIFO as a as RAN of our network processor, and to generate a signal named stop in ready to refuse the input packet from the net FPGA. And in payload, when the end of the packet signal is set, we will set the CPU mode signal. And when we are in the pre-CPU state, we will set the stop in ready signal. And so, um, so this is our network processor integrated with the convertible FIFO. And so here you can see we have 4 states, and this is our software hardware register. And so there are basically 2 parts. Uh, So first is the data pass in the FIFO mode. Um, so it is so we basically extract the drop FIFO Verilog code to here, and then is the controller, which is basically the financial state machine that I introduced, and we add the mode switch signal here, and as you can see here, only if the state goes into the pre CPU state, the CPU mode next signal is set and the stop and ready signal is set. And we will use this CPU mode signal to select the data from the uh, net FPGA data pass and the network processor pass. Um, and we haven't verified it in the net FPGA platform. So in the next week, I will verify it in the net FPGA platform, and to complete it. Um, okay, that's it. Thank you.